Hey guys, the next video that I'm going to link you guys into or share with you guys is actually a video that I recorded for my Chemistry 151 class or Gen Chem 1. As it turns out, you guys are learning the exact same information that they are learning. So instead of creating a whole new video, I'm just going to link you into their video. The video is going to show this slide right here. Well, this is not your chapter 1. The information for you is going to be found in chapter 7. So this is part of our chapter 7 chemical quantities section. But it's the exact same information. So I'm going to go ahead and link you guys into that video now. And you can listen to it and it'll be the same information. Okay, so the last thing that your chapter 1 talks about is it brings back this idea of dimensional analysis, but it applies it to chemistry-related problems. So we're going to get introduced to the mole, we're going to get introduced to Avogadro's number, and then we're going to do some more dimensional analysis. Counting numbers. So counting numbers are something that we use in everyday life. We just don't realize that we use it in everyday life. So if I said I have a pair of dogs, how many dogs do you picture? Or if I said I have a pair of penguins, how many penguins do you picture? Well, you're probably picturing 2. So the word pair is a counting number. I say pair, you see 2. That's a counting number. Another example of a counting number is one that we see here in this recipe. So recipe for deviled eggs. It calls for 1 dozen eggs. So this recipe calls for 1 dozen eggs. How many eggs are you going to use? You're going to use 12, yeah. So a dozen doesn't have to talk about eggs. It can talk about anything at once. So if I say that I have 1 dozen dogs, how many dogs do I have? Yeah, I have 12 dogs. So I say a dozen, you picture 12. And then lastly, a counting number that you probably don't use on an everyday basis, but certainly something that we can quickly figure out what it means. So here in Gettysburg, here's the Gettysburg Address, 7 years ago. So if I tell you that a score equals 20, when they started out with 7 years ago, how many years ago were they talking about? 4 times 20 is 80, and then the 7, so 87 years ago. Again, score doesn't have to talk about years. So if I say I have a score of dogs, how many dogs do I have? I have 20 dogs, yeah. If I have a score of apples, how many apples do I have? I have 20 apples. So a score is also a counting number, one that you probably were not terribly familiar with, but we got comfortable with it pretty quickly. So in chemistry, we use counting numbers as well. So let's say this safety pin was made of pure aluminum. So how many aluminum atoms would fit on the very tip of this pin? Not a trick question. The answer is D. So a lot of atoms would fit on the very tip of that pin. And that's just the tip of the pin. Imagine all the atoms inside the whole thing. Okay. So counting numbers are helpful because they reel in bigger numbers and help make them a little bit more user-friendly, easier to picture or imagine. So if we use the counting numbers that we've talked about so far, it doesn't really help us a lot in chemistry. So if I talk about how many pairs of atoms are on the end of that pin, still a ridiculously large number. If I talk about how many dozen or how many score of atoms are on the end of that pin, still lots and lots of zeros in those numbers. So it really doesn't make them any more user-friendly. So when we're talking about things in chemistry, it seems like we might need a new counting number, one that encompasses a larger amount of things. So the counting number that we use in chemistry is called the mole. 1 mole is 6.022 times 10 to the 23rd things. So I could have 1 mole of dogs. How many dogs do I have? Somebody always says too many. No such thing. But I have 6.022 times 10 to the 23rd dogs. If I have 1 mole of socks, how many socks do I have? Probably enough to fill up whatever building you're sitting in right now. So 6.022 times 10 to the 23rd socks. So a mole could count anything. Well, what kind of things do we want to count in chemistry? Unfortunately, we don't count dogs. But in chemistry, we count things like atoms and molecules and particles. So I might say something like, I have 1 mole of atoms, which is 6.022 times 10 to the 23rd atoms. And then the other word that you saw pop up here on my screen was Avogadro's number. So this 6.022 times 10 to the 23rd is called Avogadro's number. So that's where that word came from. So I very strategically wrote out this number to look like something that we've seen before. So the way that I wrote out 1 mole equaling 6.022 times 10 to the 23rd things, it should make you think about an equality. And that's exactly what it is. It's an equality. We can use equalities to help us convert from one unit to another. So remember, the application of the equality is the conversion factor. So I write mole on top, things on bottom, or things on top, mole on bottom. So we have 2 conversion factors that come out. The only thing that's different about this conversion factor is the fact that the unit can change. So before we saw things like inches to centimeters, or we saw things like grams to pounds, and those units were just there. Now we can go from moles to atoms, or moles to molecules, or moles to dogs. Number of dogs, I should say. So that unit, things can change, but the problem will tell us exactly what that unit should be. So it's not really that difficult. We just use the problem to tell us what that unit is. Okay. So what I want to do now is I want to just very slowly go through an example with you. So how many atoms are in an elemental sample of 22.9 moles of mercury? This is simply a unit conversion problem. So for every unit conversion problem we're ever going to do ever this semester, what's the first thing we always do? We write down the information that's given. We write down the number that was taken. So I'm going to write down 22.9 moles of mercury. And this right here, MOL, is just the shorthand for MOLE. Why we can't be bothered to write the E, I don't know. We're lazy chemists. But if you see MOL, it's just the shorthand for mole. All right, so back to our problem. We write down 22.9 moles of mercury. We draw our train tracks. And just like every other unit conversion problem, we let the units guide us. So what unit are we trying to cancel? What unit are we trying to get rid of? The unit of mole. So that goes down here on the bottom. So mole on top, mole on bottom. That cancels out. And what unit are we interested in? What unit is it asking about? It's asking about atoms. So that's going to go up here on the top. All right, our units guided us. We've got our problem set up. Now we just need to click back to our equality to find out what numbers go where. For right now and for the next few chapters, the number 1 will always be attached to mole. So anytime you write down the unit of mole, the number 1 will be attached to it. So mole is on the bottom. That's where my number 1 goes. So things, in this case, our things is atoms. So what number is attached to atoms? Avogadro's number is attached to atoms. So up here, I'm going to write 6.022 times 10 to the 23rd atoms. So to solve this problem, we solve it just like our other dimensional analysis problems. We multiply across the top, divide by anything that's on the bottom. So plugging it into my calculator, I'm going to plug in 22.9 times 6.022 times 10 to the 23rd, and then divide by 1, and my calculator spits out the following. Okay, so let's talk a little bit more about this calculator output. So first thing I want to talk about is this right here. So E25 is the same thing. It means the same thing as times 10 to the 25th. This part of the number often gets missed. For some reason, you start looking at sig figs and you forget to look all the way to the end. So we always want to ask ourselves, does this answer make sense? And we'll do that when we finish, so you can see kind of an easy way to not forget about that. Okay, so that's the first thing I want to talk about. The second thing I want to talk about is sig figs. So we still have to consider sig figs. And where do we go to consider sig figs? We always come to this first number that we wrote down here, the measurement that was taken. So this guy has 3 significant figures. So that means my answer can only have 3 significant figures. So the answer that I will report would be 1.38 times 10 to the 25th atoms of mercury. Okay. Now, back to that. Does this make sense? You guys probably aren't terribly familiar with a mole yet. So what does 22.9 moles look like? We don't really know yet. We got to get more comfortable with it. But would it make any sense to say I have 22.9 moles and that equals 1.38 atoms? No, that doesn't make any sense. 1.38 atoms is essentially nothing. So that wouldn't make any sense at all. When I'm counting the number of atoms, I would expect that number to be really, really big. Atoms are tiny. So does it make sense that I would have a ridiculously big number like 1.38 times 10 to the 25th? Well, yeah, that number makes sense. So always take a step back before you circle your answer and say, you know what? Does this make sense? Okay. So here is another example. What I want you guys to do is go ahead and pause the video, work through it, see if you can get to an answer, and then I will work through it quickly with you as well. All right. So how many moles are contained in a sample of 5.95 times 10 to the 22nd atoms of ES's Einsteinium, one of my favorite elements? All right, so dimensional analysis problem. What's the very first thing that we always do for every dimensional analysis problem? Write down the measurement that was taken. So 5.95 times 10 to the 22nd atoms, Einsteinium. Dimensional analysis, let the units guide our problem. So what unit is going to go on the bottom or diagonal? Atoms of Einsteinium. And what unit are we interested in? We're interested in the moles. So moles of Einsteinium. What number always goes with the unit mole? The number 1. And what number is going to go with atoms or things, that's going to be Avogadro's number. All right, multiply across the top, divide by the bottom. So 5.95 times 10 to the 22nd times 1 divided by 6.022 times 10 to the 23rd. And I get 0.0988804, yada, yada, yada. Okay. What is the number that I'm going to report? Go back to our original measurement. I see 3 sig figs. So I can simply report 0.0988 moles of Einsteinium. Okay. Does that make sense? Yeah, it does. The whole purpose of a counting number, the whole purpose of the mole is to make these numbers a little bit more user-friendly. I would much rather deal with the number 0.09 than deal with the number 5.95 times 10 to the 22nd. That's a lot to keep track of. So the fact that this became a user-friendly number, just a simple decimal number, tells me that this answer does in fact make sense. The other thing that I want to address, I'm going to write this in red because it's wrong. But the other thing I want to address is if you got a number, something like 9.88 times, gracious, it's not writing down there. So 9.88 times 10 to the 40 something. So we'll say 46th. This number came out just because of the way that you typed it into your calculator. So if you got a number that spit out like this, make sure that when you divide by Avogadro's number, that you put it into parentheses. If you do not put it into parentheses, your not so smart calculator will take 5.95 times 10 to the 22nd divided by 6.022, then it'll multiply times 10 to the 23rd. So it'll add the exponents instead of subtracting the exponents. So it's just your calculator just didn't do the steps in the right order. So if you got a number like this, just make sure that you kill it with parentheses as you type it in. All right, so in the slideshow, what I have here is just a couple more examples that you can work through on your own time. And on the very next slide, I'll click over here. We've got the answers to those problems, so you can work them out on your own time, and then instant feedback. Did you get it right? Did you get it wrong? So that ends this portion of the math in chapter 1. In the next video, we're going to relate this to measurements that we can take in the lab.